Now we will start with the study of second type of the mirror, and that is spherical mirror. First we will see how the spherical mirror is manufactured. Spherical mirror is created by using hollow glass sphere. Consider this as hollow glass sphere. If we cut this glass sphere like this, and if we separate this part, we will get a bowl-like structure. We'll get a bowl-like structure. Now, one side of this bowl we have to paint, or we have to put a coating on it, and depending on which side of this glass is coated, there are two types of spherical mirrors. So, if I put this glass like this curve, and if I give coating on this part, that is outer part, and we use inner part of this glass for reflection, then this mirror we call as concave mirror. This mirror we call as concave mirror. Now, if we put coating on the inner side of the glass and use outer part of it for the reflection, we call this type of spherical mirror as convex mirror. So this will be concave mirror, where inner part is used for the reflection and outer part is coated, and this is convex mirror, where inner part is coated and outer part is used for the reflection. Now, before going to details in this convex and concave mirror, we will study some basic terms related to spherical mirrors. Now here we saw that this was the hollow glass sphere. We cut it like this, but this was the part of this hollow glass sphere. Now we will study some basic terms related to this. Now consider this as our mirror, and we give coating on its outer part. So it will become our concave mirror. Now, if we consider exact midpoint of this mirror, we denote it by symbol P, and meaning of this P is pole. We call it as pole of the mirror. We call it as pole of the mirror. Now, this spherical mirror was part of this hollow sphere, and if we consider center of this hollow sphere, we denote it by symbol C, and meaning of C is center of curvature. Center of curvature. Now, as this sphere has a center C, center of curvature, if we consider radius of this sphere, we denote it by symbol R. And what is meaning of this R? R is radius of curvature. R is radius of curvature. If we draw a line joining C and P, C is center of curvature, P is pole of the mirror. If we draw a line which joins C and P, we call this line as principal axis. We call this line as principal axis. Now we are using this inner part of the mirror as a reflecting surface, and suppose parallel light rays parallel to principal axis, light rays which are parallel to principal axis, if they incident on this inner side of the mirror, they will reflect from this side and they will combine into one point. That one point will lie somewhere here. We denote it by symbol capital F. So if we draw a one parallel line like this, it is a parallel ray which is incident on this mirror, it gets reflected and it passes through focus. So all the parallel rays which are incident on this mirror, they combine at this point, and that point is denoted by capital F, and we call that point as principal focus. We call that point as principal focus. So these are some basic terms. P is pole, which is exactly the midpoint of the mirror. C is center of curvature. It is the center of the sphere by which this mirror is created. R is radius of curvature. It is radius of the sphere by which this mirror is created. Then line joining C and P, that is center of the curvature and pole of the mirror, we call that line as principal axis. If light rays parallel to principal axis are incident on this mirror, they get combined into a single point, and that point we call as F, principal axis. Now distance between P and F, pole and focus, we denote it by small f, and meaning of this small f is focal length of the mirror. Focal length of the mirror. Now you can see this CP distance is R, radius of curvature, and this FP distance is F, focal length. So what is the relation between F and R? What is the relation between focal length and radius of curvature? So we can write this relation as focal length F is half of the radius of curvature. Always remember this, focal length is half of the radius of curvature. Now once we understood all these concepts, now we'll go in detail about these two types of mirror, and we will see how image formation takes place in case of concave mirror and in case of convex mirror. Now we will study these two types of spherical mirrors. One is a concave mirror and second is a convex mirror. Now we'll first consider the case of concave mirror. Suppose this is a concave mirror. This is pole of the mirror. Consider this as center of curvature. Line joining C and P, we consider it as a principal axis of this. Light rays, if light rays parallel to principal axis are incident on the reflecting surface of this concave mirror, they will be reflected back, and all rays will combine in a single point, and we already studied that point is called as principal focus of that mirror. So how this will happen? This rays will incident on this concave mirror, they will reflect and they will combine into a single point. They will combine into a single point. And this point we call it as capital F, that is principal focus. So as these parallel rays are combined into a single point after reflection, we call concave mirror as converging mirror. we call concave mirror as converging mirror. As its name suggests, converging means it converges or it combines all the rays after the reflection. Now, what will happen in case of convex mirror? Suppose this is pole, and we'll draw a line like this. Suppose this is C, that is center of curvature, because this mirror will be a part of the sphere on this side, so center of curvature will go there. Now, if light rays parallel to principal axis are incident on this reflecting side of convex mirror, they will diverge. That means after reflection they will go in different directions, so they will not combine in a single point. So how we can define principal focus in case of convex mirror? So here this rays will diverge, but they will diverge such as if we trace back those diverging rays, they will combine into a single point. So let's see how this will happen. So you can see these white colored parallel rays are incident on the reflecting surface of convex mirror. They are reflected in this orange colored rays, and if I extend those orange colored rays in backward direction, they combine into single point, and this point we call it as principal focus of the convex mirror. So, principal focus of the convex mirror is not actually present there, or light rays are not actually combining there. They are appeared to be combined behind the convex mirror. So, in this way, we can define principal focus of concave mirror, which is situated at the left hand side of the concave mirror. And here principal focus is situated at the right hand side of the convex mirror. As here rays are getting diverged, we call this convex mirror as diverging mirror. We call this convex mirror as diverging mirror. Now we are going to study concave and convex mirror into details. That means if we put object somewhere on this concave or convex mirror, how its image will be appeared. That image will be bigger than the object, smaller than the object, it will be erected, it will be inverted, it will be real image or it will be virtual image. All the points we'll study in the next topic. Now, before going to study image formation by concave mirror and convex mirror, first we will study sign convention. While drawing ray diagrams, we have to follow some sign conventions. All of you must be knowing the Cartesian coordinate system. In Cartesian coordinate system, we draw two perpendicular axes like this. We call this horizontal axis as x-axis. We call this vertical axis as y-axis, and their point of intersection we call it as O, that is origin. We know on this x-axis, if we go on this side, that is right side, all the values are positive. If we go on the left hand side of the x-axis, all the values are negative. On the y-axis, if we go in the upward direction, all the values are positive. And if we go in the downward direction of y-axis, all the values of negative. If you know all this system, you can easily replicate this system or use this system in sign convention of image formation in mirror. In mirrors, we consider principal axis as x-axis and mirror as y-axis, and surely their point of intersection will be pole. So whatever values we measured in the right direction of this mirror, we consider them as positive, same like this Cartesian coordinate system. Whatever values we measured in the left side of the mirror, we consider them as negative. Whatever values we measured in the upward direction from the principal axis, we consider them as positive. And whatever values we measured in the downward direction from this principal axis, we call those values as negative. Now, if I consider a concave mirror, so while ray diagram we have to follow certain rules. We know for this concave mirror, here there will be pole, here there will be focus, and here there will be C, that is center of curvature. Now whenever we draw a ray diagram, we always keep object on the left hand side of the mirror. Please remember this, we always keep object in the left hand side of the mirror. So object will always be here on the left hand side. Distance between object and mirror, we denote it by symbol U. We call it as object distance. We call it as object distance. Now, its image may be formed on the left hand side or right hand side. Suppose image is formed somewhere here. Now, distance between image and pole, distance between position of the image and pole, we call it as symbol V, and V is image distance. V is image distance. Now, this is focus or principal focus, this is pole. We know that distance between F and P, we denote it by small f, and small f is focal length. Small f is focal length. If we consider height of this object, we denote it by symbol h1. And we consider height of this image, we denote it by symbol h2. So I will revise it again. U is object distance. Object distance is distance between object and pole. V is image distance. It is distance between image and pole. Small f is focal length. It is distance between principal focus and pole of the mirror. Height of the object, we denote it as h1, and height of the image, we denote it as h2. Now, depending on this sign convention, this all values will have some signs. Now, we will study what are those signs. We will start with object distance. Now, as you can see, object is always kept on the left hand side of the mirror. This object distance will be always negative. So U always negative. U always negative. Now we'll see image distance V. Sometimes image is formed on the left side of the mirror. We call that image as real image, and sometimes image is formed behind the mirror. That means on the right hand side of the mirror, we call that image as virtual image. So V will depend on two factors. If image formed is real and if image formed is virtual. If image formed is real, then V will be negative. If image formed is virtual, then V will be positive. Now we'll study focal length F. Now for focal length, it depends on the type of the mirror. For concave mirror, we saw that focus is on the left hand side of the mirror. So this focal length will be negative. And in case of convex mirror, focal length always lies in the right hand side of the mirror. So for convex mirror, we consider F focal length as positive. Now we'll see what will happen with this H1 and H2. Now this H1 is size of the object, and we always keep object in this erected position. So this H1 will be always positive. This H1 will be always positive. Now what will be the size of the image? Again, there are two types of the image. One is inverted and one is erected. Erected means it is standing like this, and inverted means it is in the downward direction. So H2 will depend on two things. If image is erected, that means pointing in upward direction, we will consider H2 as positive, and if H2 or image is inverted, that means pointing in the downward direction, we will consider H2 as negative. So by using this sign convention, we can remember all these values or all these signs of U, V, F, H1 and H2. Recently we studied sign convention in case of image formation in spherical mirrors, and we saw different signs to be used for U, V, F, H1 and H2, where U is object distance, V is image distance, small f is focal length, H1 is size of the object, and H2 is size of the image. Now, depending on different situations, depending on different conditions, we give different signs to these variables. Now we'll see how this U, V and F are connected to each other. U, V and F are connected to each other by a very important formula. We call that formula as mirror formula. And the mirror formula is 1 upon V plus 1 upon U is equal to 1 upon F. Mirror formula is 1 upon V plus 1 upon U is equal to 1 upon F. This mirror formula is true for both types of the mirror, that is convex mirror and concave mirror. But whenever you will put the value of U, V or F, you have to consider the sign conventions of these variables. That means as we keep object always on the left side, u will be always negative. For concave mirror, f will be negative. For convex mirror, f will be positive. In case of v, for real image, v will be negative. For virtual image, v will be positive. So we will keep u, v, f values with their signs. Now, one more formula in case of mirror we use is power. Now, what is the power of the mirror? Power of the mirror formula we use is P is equal to 1 upon F. Formula for power of the mirror is P is equal to 1 upon F. What is the power of the mirror? Power is ability of that mirror to converge or diverge the rays. Power means ability of that mirror to converge or diverge the light rays. So now here you can see formula for power is equal to 1 upon F. That means it is reciprocal of focal length. So if you consider a concave mirror, this is principal axis, this is pole, focus and center of curvature. Now, if we consider focus here, distance between P and F is small f. If we consider focus here, rays will come like this. They will incident on this surface. This part of this mirror will be coated. Rays will be incident on the reflecting surface. They will turn back and they will go through the focus. They will go through the focus. So by this value, this ray is converged. Now you can see if focal length is less, power will be more. So now if we decrease the focal length, that means instead of here, if I consider focus here, this ray will be converged like this. So here converging of this ray, previously it was this much, and now after decreasing the focal length, the converging of the rays was this much. So now as decreasing the focal length, the ability of that mirror to converge the rays is increased. That means its power is increased. Now what is the unit of this power? If we express F in meters, we express power in diopters. Now, as you know, the focal length of the concave mirror is negative, so its power will also be negative. Focal length of the convex mirror is positive, so its power will also be positive. One more formula in case of mirror we always use is lateral magnification. And formula for lateral magnification is M is equal to V upon U. We use one more formula, this lateral magnification, and that formula is H2 upon H1. That is size of the image upon size of the object, and V upon U is image distance upon object distance. We can take a very simple example of this. If we use a pencil as an object and its size is 3 cm. So we will consider H1 as 3 cm. We use some mirror and we obtain its image of size 15 cm. So our H2 will be 15 cm. So what will be the value of M? Size of the image will be 15. Size of the object will be 3. So 15 upon 3 is 5. That means that mirror magnifies the image 5 times. So whenever we use any object, its 5 times bigger image will be created by that mirror. So in this way we can define this lateral magnification. So we studied 3 formulae. One is mirror formula. It is 1 upon V plus 1 upon U is equal to 1 upon F. Remember, while putting the value of U, V and F, you have to use the sign convention. Then we saw the formula for power of the mirror. It is P is equal to 1 upon F. If we express F in meters, we write P in diopters. As we decrease the focal length, ability of that mirror to converge or diverge the rays increases. That means power increases, and we express the power in diopters. And the last formula is lateral magnification. Lateral magnification formula, small m is equal to V upon U, that is H2 upon H1, and we studied it by a very simple example. If we consider the object is of 3 cm, its image appeared to be as 15 cm, their ratio 15:3 will be 5. That means that mirror will always create 5 times bigger image of the given object. Start with the next topic, that is image formation by concave mirror. You already studied this topic in standard 9th with 6 various conditions and 6 various rays diagram. Now here the same concept is used in your 11th standard chapter, so we'll again revise it. I will give you a small trick also to remember all these 6 conditions. Now consider this as a principal axis, this as a mirror, and suppose it is concave mirror. It is concave mirror. Now this will be pole, this will be focus, and this will be center of curvature. Now as we know, distance between P and F, we call it as small f, and distance between C and P is radius of curvature, so we denote it by capital R. And we know relation between capital R and F. F is half of R, that is focal length is half of radius of curvature. So we can say that radius of curvature is double the focal length. So if we consider this distance as F, then we can consider this distance as 2f. We can consider this distance as 2f. Now we will study 6 different conditions. That means where or on what position the object will keep, and according to that on what position its image will be created and what will be the nature of that image. So we will complete this table according to this diagram. So first we'll start with infinity. If you keep object at infinity, that means in position of object, you will write U is equal to infinity. Its image will be created at focus. Its image will be created at focus. So actually infinity is a very large distance, but for just a sake of simplicity, I drawn that image, that object here outside this diagram. You can take the meaning of this as infinity. That means object is kept at infinity and its image will be at focus. Its image will be at focus. Now you will see that I only drawn a small dot as an image. It denotes the size of the image. That image is a very small image, or we call it as a diminished image. So if object is kept at infinity, its image will be created at focus. As this image is on the left hand side of the mirror, it will be real image, and as this image is very small, we use word that image is highly diminished. That means its linear magnification will be 0. Its linear magnification will be 0. Now we'll form a simple trick here. What we'll do, we'll bring this object closer to the mirror gradually, and its image will go away from the mirror gradually, and while image is going away, its size will increase. So if you keep this trick in mind, you can easily complete this 6 conditions. This will be our first condition, that if u is equal to infinity, v is equal to f, image will be real and magnification will be 0. You know the formula for magnification, v upon u. So v is f, u is infinity, f upon infinity will be 0. Now I will bring this object closer to the mirror, and now I will keep this object here. You can say beyond C, or we use one more term, that is beyond 2f. Beyond 2f. So what will be our second condition? Second condition will be u greater than 2f. So object distance will be greater than 2f. Now I already told you the trick that this image will go away from the mirror. So previously image was at focus, now it will go slightly away from the mirror, and the image will be formed in between f and c, and I also told you that its size will increase gradually. So here it was a point image, now its size will slightly increase. Its size will slightly increase. I will give numbers here. This was our first condition, and its image is formed here. This was our second condition, its image formed here. So here you can see image is formed between f and c. That means this is in between f and 2f. So you can write v, which is greater than f and less than 2f. Now as this image is again formed on the left hand side of the mirror, this will be real image, and as you can see size of the image is smaller than the object, so magnification will be less than 1. Magnification will be less than 1. Now we'll go for third condition. I will bring this object again closer to the mirror. So now I will keep this object on C. This will be our third condition. This will be our third condition. Now according to our trick, image will again slightly go away from the mirror and its size will increase. Previously its size was this, that it was smaller than the object. Now it will slightly move away from the mirror, its size will increase, and here its size will be exactly as that of object. Image will be formed at C, image will be formed at C, and its size will be same as that of object. So I will give here number 3. So third condition I will write, when u is equal to 2f, v is also equal to 2f, image will be real, and m is equal to 1. What is the meaning of m is equal to 1? That means size of the object and size of the image are same. Now again we will go ahead, we'll move this object slightly near to the mirror, and now we will keep this object in between C and F, and as per our trick, this image will again go away from the mirror and its size will increase. So this image will go away from the mirror and its size will increase, and now it will be greater than the object. Now it will be greater than the object. So here I will give numbers. Fourth condition, here it is our fourth condition, this is our third condition. Now I will write this here. Fourth condition, that u will be greater than f but less than 2f. So object is kept in between f and 2f. So I written u greater than f and less than 2f. Its image will form after the 2f. So v will be greater than 2f. Again image will be real, and here now magnification will be greater than 1, because now size of the image is more than the size of the object. Now we'll again move forward. This object will keep now on focus. If we keep object on focus, its image will be formed at infinity. Here I shown infinity here. So this will be our fifth condition, and size of the image will be very big, or we can say it is highly magnified. So we can write fifth condition. We can write fifth condition that u is on the focus. So u is equal to focal length. Image will be formed at infinity. So v is equal to infinity. Again the image is on the left hand side, so it will be real image, and magnification will be very large, we can say infinity. So you know the formula of f is equal to, m is equal to formula of m, you know, m is equal to v upon u, value of v is infinity, value of u is f, so infinity upon f, answer will be infinity. Now for this 5 conditions you can use this simple trick. Bring object closer and closer to the mirror. Image will go away from the mirror gradually, and while going away its size will increase gradually. So by keeping this simple thing in mind, you can remember all these 5 conditions. But I told you there are 6 conditions, but our 6th condition is exception to this trick. If we move this object more close to this mirror, suppose I keep this object here, this will be, we will call this as within the focal length. The 6th condition will be that we keep object within the focal length. So we'll write 6th condition here. That u less than f. U less than f. So here this trick will not be followed. Its image will not be formed on the left hand side. Its image will be formed behind the mirror. Behind the mirror. Its image will be formed behind the mirror. So when u is less than f, then here this will be image distance, this will be object distance. Object distance v will be greater than u. Mod values. So mod of v, that means absolute value of v is greater than absolute value of u. So this distance will be more than this. As image is formed behind the mirror, this image will be virtual, and we will get this image as magnified image. So value of m will be greater than 1. Value of m will be greater than 1. So by this table you can easily remember image formation by concave mirror. You already studied these 6 conditions in your 9th standard. We revised it again, and this is used as it is in your 11th standard chapter syllabus. Now, what will be the image formation by convex mirror? What will be the image formation by convex mirror? We don't have to study this much conditions for convex mirror. So, in case of convex mirror, image formation is very simple. Suppose this is convex mirror, this part is coated and outer part is used for the reflection. Here focus will be behind the mirror. Now, there are two simple conditions. If you keep object at infinity, that means when u is equal to infinity, its image will be created here. You can see I just put a dot, that means size of the image will be very small. Point size image will be created. So I will say V is equal to F. As image formed is behind the mirror, so nature of this image will be virtual and this image formed will be erected. Now, if we keep this object anywhere between infinity and pole, its image will be created between pole and focus. Its image will always be created. Suppose I keep object anywhere between infinity and pole, its image will be created between P and F. As you can see, this image is behind the mirror, its nature will be virtual. Its size will be less than the object, so it will be diminished, or its size will be small than the object. We say that image is diminished. So it will be virtual, diminished and erected. So in case of convex mirror, the answer is very simple. If you keep object anywhere, its image will be virtual, image will be erected and image will be smaller than the object and it will always be created between P and F. So we completed image formation by convex mirror and concave mirror. So here we will end with the part reflection of light. All these topics which you studied up to this, they are already covered in your 8th and 9th standard chapter with the name reflection of light, and they are included as it is in the chapter optics of 11th standard. So here we completed with the part reflection of light. In next part we will start with the refraction of light. Thank you.